Hey there, we're going to be doing the second style of thermochem problems on the worksheet, with which primarily use the concept of H equals mCp delta T. So the first question we're doing here is a heat curve problem, and the important information that we're given in the problem is that we are starting at 50 degrees and we're going to negative 48. And so one of the first things you want to do here is you want to sketch yourself a little bit of a, which I've inserted into this document here. We're just going to move it over to the side here. And again, the important things that you want to try to match up in this case are the fact that we have 50 degrees in the problem, so we set that as the maximum in this case. We have negative 48, which is obviously lower, and we're setting that as the minimum. And that tells us that we're going to ignore the 357 since it doesn't fall in between those two temperatures, and we're specifically using the negative 38 there as the value on the y-axis. Okay, so once we have that all sketched out for ourselves, what we want to do is we want to go ahead and figure out the equations that we're going to use in the different sections. So here I've labeled this out as Q1, Q2, and Q3. So again, I'm hoping that you see that the Q1 pertains to this right here. And sorry that my arrows do that occasionally, but we're going to try to get that corrected. And if I can't, then I can't. Okay, so we're going to just do it by freehand here. So this Q1 right here obviously pertains to that section. This Q3 pertains to this section, and then Q2 down here pertains to the plateau. And since we are going from solid to liquid, it's a fusion value. So again, it's sort of a process of elimination. We're not going to use anything with vaporization. We're not going to use anything with boiling point. We're not going to use anything with the gaseous H2O, sorry, gaseous mercury. It's all about freezing point, fusion, and liquid and solid. So we're going to nudge these graphs up a little bit so we have room at the bottom of the screen, and then it's just a matter of finding the numbers to plug in. So the first value I'm going to do, or the first calculation I'm going to do, is going to be Q1, and that's my mass, my heat capacity of my solid, my heat capacity of my liquid, and the delta T between 50 and negative 38.72. I think it is important to remember that that difference right there is the difference between a positive and a negative number. So you got to do that mathematics out correctly and make sure that you recognize it's minus a minus 38.72. The next part of this problem will be doing the calculation for the Q2, and that Q2 value will be a state of matter change, so there's no delta T, just 33 times the heat of fusion. And I'm going to be using the joule per gram value there at the top, just because that's the easiest one to use with the units that I have, right? Joule per gram of fusion there. And then the third calculation is going to be that we're going to do Q3, which is when the mercury is a solid. And so again, we have some negative signs there that we're dealing with in the delta T. So you're just going to be careful about setting up those negative signs as I referred to back over here in Q1, and make sure that you do them correctly, right? That means that the last step of the problem is simply to add these Q's together, and you get your total Q, which in this case is 941.1 joules. The next problem that we're doing is question number 4. We're back to water here, so easier than the number 3 that we just did. We've got a temperature of 45 degrees Celsius, and we're told that we're going to ice at 0 degrees. So the important part of that information is that we know we're going through a state of matter change since we're converting it from liquid water into solid water. So that means we're going to have 2 different Q's here. Q1 is going to be the one that is associated with the delta T, right, of 45. And then Q2 is going to be the one that is dealing with the heat of fusion, which again is on your heat of formation chart on the backside. And so by using those two right there, we're going to simply calculate those and add them together. And the total is, in this case, equal to, sorry about that, That's just at the very bottom of the screen there, so hopefully we can move it up. There we go. So the total is 26,184 joules. Next question we're doing is number 10, which is a sort of a word problem that deals with a heat produced by a substance, in this case KMnO4, which is dissolving into water, right? 50 grams of water. So what we're going to do here is, the first thing is we're going to figure out the heat that it has lost. And the heat that is lost deals with the mass of the water, the heat capacity of the water, and the change in temperature that we get from the problem. That Q value is equivalent to 292.6 joules. Okay, so that's the first part of the problem. The second part of the problem is to sort of look at the fact that we are given a mass of a substance. And so what we have to do there is determine how many moles of that substance we have, right? So we're going to find the molar mass of the potassium permanganate, and we're going to convert the 1.10 grams into moles, and in a moment use that value. And the way we're going to use that value is we're simply going to take our value of Q, which is in joules, and our value of moles, and do a ratio, because that's what we're looking for when we find delta H, right? Delta H is usually in kilojoules per mole. So what we're going to do in this case is we're simply going to say 292.6 over the number of moles gives us a value of joules per mole, and then I've gone ahead and converted it into kilojoules per mole. You certainly could, in this question, express it as a much bigger number of 42,000 joules per mole. And then the last question of this type on this worksheet is number 13. And what we're going to do in number 13 is we're going to be mixing some very hot silver, in this case 350 degrees Celsius, with some water that's close to room temperature. And I think the important thing to understand in this case is that the silver is going to lose heat, the water is going to gain heat. So what we're going to essentially do is on either side of that equation use the concept of MCP delta T. So we've done one of these in class that's sort of very similar. I don't think we used silver, we used water in both cases, but it's the same concept. You've got the value of silver on one case, right? Mass and heat capacity. Remember, we articulated this value right here as always being high minus low, and ditto on the right-hand side, it's high minus low. So it's just important to remember that the 350 degrees silver is going to cool down and the 30-degree water is going to heat up. Probably the most challenging part of this is the solving of the algebraic equation. So in the end, T2 will turn out to be equal to 31.8. You just have to take your time with the solving of the equation, right? You're going to probably multiply these two together. You're going to multiply these two together. And then you might do a little bit of combining in that case, or you might do some distributing to the parentheses, and then you just got to sort of power through it algebraically until you get the answer of 31.8. Okay, I hope those help you in working through these kinds of problems.